with the machine learning course, chapter 3, but as a student pointed out, and I'm glad you reminded me to tell you, I'm putting up the Splunk SOAR project. One of my corporate customers wants me to teach a class in Splunk SOAR. And so the first 2 projects are now up, and there's a scoreboard, and you can get extra credit in any of my classes by testing these out, which would help me. So I make sure everything is like cleaned up for my corporate customers, and there will be a bunch more. All you do here is install the products, which turned out to be a lot more difficult than I thought it would be, but I will follow this by a whole lot more projects. Using Splunk SOAR. Splunk SOAR is security orchestration, and this is a system that will automatically detect intrusions and automatically respond to the intrusions. So it's really quite important, and it really belonged to my classes anyway. That's why immediately when the corporate customer wanted this, I said, well, I really should do that anyway. Just for my City College students and just for everybody, I ought to learn how to configure and run Splunk SOAR. So I'm going to do it, and I'll accumulate it on my homepage, and you can get extra credit in if you like. Anyway, so here we are. This is machine learning, and we're down to the 3rd class, which is classification. So let's start talking about that. This I found very interesting. I like everything about this. That's why I decided to teach this pirate course. Machine learning is very interesting, and it has made huge strides since I did some very primitive forms of it 30 years ago, 35 years ago. I'm really glad to learn the modern version of it that actually works. When I did it, it was kind of useless. So this is pretty much following a project, ML 105, that goes through pretty much all these steps. The last couple aren't there. But anyway, so the first thing you have to do is get some data. And here we use the same data we used before, 70,000 images of handwritten digits, which you can get with just a couple of commands in Python, which we've done in previous projects. Now let's see. ACOE is hiring for security roles. Okay, well, that's good. There's a link in the chat of somebody that wants to hire for security roles. That's great. All right, good. I see some useful information in the chat, but I don't think I need to comment on it much. Anyway, so now when you define this, it has 2 parameters, x and y. X has the pixel values, so if you set x, y equal to the MNIST data, then you can print x, which is kind of cool. I didn't know about this. If you print something that's really huge, it doesn't print the huge thing, it prints a sort of summarized version. So what x is a series of grayscale image pixel values, 784 pixels per image, and there's like 70,000 images. So instead of just flooding the screen with junk, it prints a nice summary. This is 784 zeros or other numbers here. There probably aren't zeros. Some of them will be ones indicating, some of them will be up to 255 indicating grayscale. That's what it looks like, and here's the shape of it. There's 70,000 images, each containing 784 pixel values, and here's the Y. The Y is a series of digits, 70,000 of those. And what these are the labels. So you have a bunch of images, and you know the correct digit that image represents. And you can look at them, and if you do, you'll see here they are handwritten digits, and see these are 7s, that's a 2, that's an 8, but some of them are sort of scrawled, and you might, like this one here, you might get a little confused whether that's a 3 or an 8, and that sort of thing. So that's the point. It's a good machine learning task to teach the machine learning to recognize the digit from this. So you break the data up into training and testing sets. The general rule is take about 80% of the data for training and 20% for testing. So here you take 60,000 of the 70,000 and call that the training set, and the rest is going to be the test set. So that defines them, 60,000 images to learn on and 10,000 to test the model on. All right. And so the first thing you can make is a binary classifier. Now, to make a binary classifier, it can't sort things into 10 categories. It can just make true or false decisions. What we'll do is true means it's a 5, false means it's not a 5. So that means, of course, both sets are 90% false because most of the digits are not 5. So you can run some simple Python commands to make your training set and testing set. And you see here, so that in the training set, I have about 5,400 true and 54,000 false. And in the test set, I have 890 true and 9,000 false. So that's just what you'd expect if there's an equal amount of each digit approximately, and that's the case. So now we can make a model. Now this is the simplest model to understand, although this is in fact a really stupid model. So suppose you take your input image, you just take all those pixels, and each pixel just feeds into a single neuron, which is linear. So it just takes a weight factor times the intensity of this thing plus an offset, 2 parameters here, 2 parameters here. So I guess, to be fair, this should probably be 784 times 2. Because there's slope and intercept for each of those. So that would be how many parameters there are. And that's probably enough parameters to do this problem. The problem is this is really stupid. If you think about this, it's just linearly tied to each pixel. So it's not clear that it's going to be very effective at doing the job here. And as we're going to see, it's not terribly effective, but it is the simplest model to start from. So I guess you could say it would notice if things up in the corner, like for a 5, it could notice if this area is white, that makes it more likely to be a 5 and less likely to be 8. So I guess it makes some sense just by looking at the intensity in various ranges, various areas of the image. It can probably learn to discriminate them to some extent. So now you have defined a classifier. Now you have to find some way to optimize it. Now there's a system called stochastic gradient descent. We'll talk about quite a bit more later, and especially next week in chapter 4. This is where you figure out what the slope is. You find some kind of cost function, and you figure out what the slope of the cost function is along all the parameters, and then you move in the direction that decreases the cost function. So it's just like a ball rolling down a hill. You're on a hill, and you just move in the direction that takes you downward. And so that's one way to do it, and here's an example of a stochastic gradient descent. If you're trying to discriminate these clear dots from these red dots, then any of these lines would do, but you'll typically pick the one in the middle with the widest border in it. So to train your binary classifier, it's incredibly simple. It only takes a couple of lines of Python. You import the stochastic gradient descent classifier, and then you train it with a random seed, and this defines it. You define a classifier, and then you just train it. Now, the cool thing about stochastic gradient descent is you don't even need to tell it how many rounds to go, because we'll talk about this in future chapters, but the simplest thing it can do is just roll down until it starts going up, and then stop, saying, well, I appear to have hit the bottom. So that simply can tell by itself when it has hit the bottom. And that's what it does here. So we fit it. It will do however many cycles it has to do to fit, and you see, in this case, it was 239 cycles it took. And then it decided, and notice the loss, 78.6, 77, and then it started going up to 77.8, so it stopped. It kept going until it went up, and then it said, okay, I must have hit the bottom. I'm going up again. So it was done, and here we are. And so we can look at some predictions. So true means the prediction is correct, and true means the image is a 5, and false means the image is not a 5. And you can see 504, it gets true, false, false, which is correct. So as you would hope, the model predicts the first 3 images correctly, so it is not terrible. It has some success at doing this. So now we talk about how you determine the performance of your model. And we've also talked about this before. We're going to use cross-validation. We're going to use 3 folds, which is up here in this parameter, and that means we're going to break the training set into 3 groups, and 3 times we're going to evaluate the model. We're going to train it on 2/3 the images and test it on the remaining 1/3, and then try it on the other combinations. That's called cross-validation, and you get 3 accuracy numbers. So the accuracy is 95% on the first fold, 96% on this fold, and 96% on that fold. So that sounds pretty good, 95% success, but it's not as good as you think it is, because remember, 90% of the images are false. So if you just called everything false, you would have 90% accuracy. So 95% accuracy really doesn't mean we're doing a great job. If you think about it, if you called everything false and you only called half of the 5s equal to 5, you would reach 95%. Now that's not exactly what the error system is here, but it still shows it's not doing an enormously good job, which is kind of what I thought. For a simple linear model, it's probably not really designed to do a great job here. And that points out that accuracy alone is not enough to give you performance, so there are better ways to measure performance. And so here you can run something called the confusion matrix, which is the whole arrangement. So here you have, these are the not 5s, and these are the 5s. and the diagonals are the correct ones. These are the not fives that were called not fives. These are the fives that were called fives. And as you can see, that's most of them. These are the not fives that were mistakenly called fives, and these are the fives that were mistakenly called not fives. And so you can see that, in fact, it is kind of close to what I said. It got almost all the not fives correct. This is only about 1% of them wrong, and it got about half of the fives wrong. So I guess now that I look at it, this model is doing what I pretty much described. It's calling everything not five and only detecting half of the real fives, and that's how it reaches 95%. That's a pretty close approximation to what it's doing. So you can define various parameters. Precision is the true positives over the true positives plus false positives. That is how likely it is when it says something is true, that it's true. And so if you measure that, you'll get 83.7% for this. 637 non-fives were identified as fives. 3530, makes me think, I wonder if I've read this matrix wrong. Maybe I should read it vertically. First row I thought was the false images, the not fives. It could be the first column, though. Now I'm a little troubled because this calculation suggests it goes by columns instead of rows. And I think this matches the book, so I might have that a little backwards. Maybe this was how many were wrong of that, and this is how many were wrong of that. That's disturbing. I don't think I'm going to stop and figure it out. It might be good to look in the book and figure out which way it is there. Let's see if this gets any better. So you can get perfect precision by classifying everything as false, except one, which it classifies as true. Then you'd have many false negatives, but no false positives. Now, I am troubled about this. Let me just open up the book and see if I can get this straight, because see if I have the Kindle. I don't seem to have the Kindle app available in my things pinned. Let me take a look at the book and see if I can understand what happened here. Because this is a big part of this chapter, is the how to measure the precision of things, and now I'm a little troubled. This is hands-on learning, and here we are in classification, performance measures. Okay, confusion matrices. Let me see if I've got this right or if I've got it turned around sideways. So there's this chart, 53,600. 1,800, yeah. Each row represents an actual class, where each column represents a predicted class. So these are the ones, the first row is the ones that were not fives, and the second row is the ones that are fives. So that was correct. Okay, so what I said before was correct. Now, the precision is here, true positives over true positive plus, the positive. Okay. So these slides are in fact correct. My explanation, I got garbled. So these are the things that are not fives in the first row. However, for precision, we want to have all the ones that were called fives. These are the false fives, and these are the true fives. So you can call these false positives and true positives. That's what's going on for precision. All right. So that's what's going on here. So that is 687 and 3530, so you get this 83%. So these are the ones that are really non-five, and these are the ones that are really five. These are the false positives, 687 non-fives were called fives, and these are the true positives, 3,500. All right. So now let's talk about recall. Recall is true positives over true positives plus false negatives. So the true positives are here, 3530, and the false negatives are here, 1891. This is the number I was talking about before, where it's these are the fives that were misidentified as fives. So recall is the number I brought up in the first description, where I see almost half of the images, or some large portion of the images, are being misidentified, and it's apparently about a third of them, they're being misidentified. Because, all right, so 1,800 were false negatives and 3,500 were true positives. So you have a 65% recall in this case. All right, so that's precision. All right, that's recall. All right, so here's another example from your textbook. If you consider just these 10 images, and you consider them in the that matrix. So here's the ones that are predicted, negative and positive, and here's the actual negative positive. So these are the non-5s and the 5s. So these are the ones that were not 5, these are the images that were 5. So all these are really 5. And here, this one was misidentified as a 5, so that's a false positive. And these are false negatives. They are 5s that were identified as something other than 5. And here's the true positives, and here's the true negatives. So this is a graphical presentation so you can understand the confusion matrix. All right. So the F1 score is a precision times recall over precision plus recall times 2. This is just a number. Now, precision and recall are fractions that go up to 1. You can also express them as percentages, and this is the same. It will go up to 1 as a maximum if precision and recall are both 1. Then this will be 1 times 1 over 1 plus 1, which is 1 over 2 times 2. So if precision and recall are both perfect, then the F1 will be perfect. But it's only going to be high if both precision and recall are high. So it's one number that might be a score that gives you a simple one-number measure of your entire, the quality of your machine learning model. And so now you can trade precision for recall, as we talked about before. If you make it very hard to detect a positive, to where you only detect one positive and it's true, then you'll have 100% precision, but you're going to have terrible recall. I think that's how it works. So here you go. If you have a neuron putting out a signal at the end, and if the signal is high, you call it a positive, and if it's low, you call it a negative. And you can define this threshold. So if you move the threshold way high, then you increase the false negatives, because it's very hard to get a signal high enough to believe it's really a 5, but then you get high precision and low recall. If you go the other way, if you make the threshold very low, then you'll call a lot of things 5s, even if they're not 5s, so you'll start having a lot of false positives, but you'll get rid of the false negatives, and that's going to get recall bigger than precision. And so with a threshold and an intermediate value, these two numbers should be approximately the same. And so you can adjust your model, and this is something you might want to do. You might want precision to be equal to recall. That might be sort of a general use situation, but I remember having this discussion many times in my security classes about biometric classifiers, which is the same issue. You have to decide your condition. For example, if this is a biometric authentication system to let you into a building, like it looks at your face and it tries to recognize your face to let you in. If it's just sort of an average security situation, you might want this. But if it's like a military base, you probably want to move the threshold up here, because you really want to make sure that unauthorized people don't get in. And you're willing to accept false negatives where the right person can't get in and put up with all the irritation of them having to go through some special process to get in, because it's more important to you to avoid false positives than to avoid false negatives. Whereas if you're like a public place like City College where you really want a lot of people to come in easily, you'd go down here where it's pretty easy to get in. And even like City College has an ID card, but it's ridiculous. If you looked at it, it looks like a small child tried to make it. It's a blurry picture off center on a crappy piece of plastic. If you just made one with a crayon, it would be almost like that. So that's a case like this where you really, whatever privileges you get from a City College ID, which I guess is maybe taking a book out of the library, I really don't know what it is, you made it pretty easy to forge. So you've made it easy for the real students to get in and pretty easy for fake people to get in. And that's what you have down here. You have very few false negatives, and you have some false positives. Anyway, all right, so there's the trade-off, right? So if you move, in this case with the 5 things, with the 10 images we talked about before, you could move up to here. If your threshold's up here, then only the true positives will get through, so your precision gets up to 100%, but the recall is only 50%. Here it's 80% and 67%. Here it's 75% and 100%. If you go down here, there's no 5s below there. So here you get 100% recall. Here you get 100% precision. And here's the spot where they're approximately equal. All right. So you can run the Python and get a complete graph of this. You can see precision and recall as you move the threshold. And as you see, a threshold near 0 makes them approximately equal here. And if you move the threshold very high, precision gets very high and recall gets very low, and down here is the other way. Up here you get some funny noise because the actual numbers are getting really small. But anyway, now here's another curve you can make. You can plot precision against recall and then vary the threshold, and you'll just get a curve measuring this thing. So that's another way to express the overall quality of your machine learning classifier. And here's one that is recommended, the receiver operating characteristic. And I guess I before E except after C. Ah, yes, except after C. There we are, now it's better. So here you plot recall versus false positive rate. This is what they do. And the point is, if you have a random classifier that just randomly says true and false, then you will get half, your false positive rate will be, you'll get a diagonal line here, where your true positives are equal to your false positives, because you're just randomly guessing. So the area under the curve for a random classifier is 0.5. For a perfect classifier, the area would be 1. You'd be all the way up here. And so you see, the more closely you hug the axes, the better your machine learning model is. And so the area under the curve can be taken as a measure of the overall quality of your machine learning model. And so here you compare a couple models. Here's the standardized gradient descent linear model we used. And remember, I said from the start, that simple linear model is probably not so good. If you use a more complex model, and one we'll talk about in later chapters called a random forest, that has a more complicated array of neurons, you can see it's much better. It's way up here, very close to the axis, much more precise. And you can calculate it. So the linear model has precision 83.7, recall 65%, F1 is 0.7, and the area under the curve is 0.96. But the random forest has got precision much higher and recall much higher, F1 much higher, and the area under the curve almost perfect, 0.998. This little bit up here is not even 1% of the area, so that's 99.8% area under the curve. So that's that forest model fits very well. So let's try a Kahoot. Let me bring them up here. I got to get to the right browser. And oh, I see some, when I say linear, yes, linear, when I say linear, what I mean is the signal from the input. The signal from the pixels is just combined here with two parameters, intercept and slope. So if the brightness goes up by a factor of 2, the signal will go up by a factor of 2, although there's also an offset. That's what each one of these, just a straight line, AX plus B, or theta 1 plus theta 2 times the input. That's the linear thing. And how does it avoid local dips? This is a very good question, ACORN. It has a problem. Standard gradient descent has a problem. Stochastic gradient descent has a problem at local dips. If you take small steps, it will just find a local dip and stay there. If you want to avoid a local dip, you have to use larger steps, but then you might overshoot, and this is a problem, and there are various ways to address it that we'll get to in the next chapter. All right, there's YouTube videos about stochastic gradient descent. Yes, very good. Good, I see that the chat is good, as it should be. You folks are right on target. So let me find my Kahoots, which will be here. All right. Yeah, you could see in that process where it just took a lot of steps, and as soon as it got a little bit bigger, it quit. That could have been a local minimum. And so that's one of the many reasons why that is not a very perfect model. Oh, I forgot to upload the Kahoots. So we'll do them later after we take a break. Wait, I don't even have them with me. All right, we're not going to do the Kahoots today. I intended to, but I can't. I forgot to load them into Kahoot, and they're not on this machine. They're on my home machine. So there will be no Kahoots today. Such is life. So we'll go on to multi-class classification. So now we really have 10 different digits. It's not just 5s and not 5s. What we'd really like to do is sort them into 10 categories. So a binary classifier just has a true or false and this one output that you compare to one threshold, so it can do a binary thing. But to do a multi-class classifier, what I want is I want to take the input, put it in pixels, I want to send it through some kind of neural net, and then I want to have 10 outputs. The probability of it being 0, 1, 2, 3, up to 9, I want to have, that's what you want. You want a 10, that's called a multi-class classifier, where it classifies it into many categories. So to make that, you can make a binary classifier into a multi-class classifier, and there's two basic ways to do it. One is one versus the rest. So you define 0 or not 0. Then you train another model for 1 or not 1, and so on, including 9 or not 9. So you train 10 models to look for each digit separately, and then you just select the class with the highest decision score. So one of these will presumably be positive, saying it is a 9 or it is a 1 or it is a 5 or something. And I guess you take the positives and you take the ones that has the highest output of being positive and you call that the winner. So it's surprising that you would do something as complicated as making 10 separate models, but that's what you do, and then combine them to make a 10 category model. And the other one is even crazier. You do 1 versus 1. So you have 0 or 1, 0 or 2, 0 or 3, up to 0 or 9. Then you have 1 or 2, 1 or 3. Then you have 2 or 3, 2 or 4. So you have 9 models here and 8 models here, because you don't need to have this one, which would be 0 or 2, because you've already got it here. And so you have a 7 here and so on. So you've got the total number is 9 plus 8 plus 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1. So that's 45. And in general, if you have n categories, it's n times n minus 1 over 2. So that's pretty crazy. You have 45 binary classifiers that you combine. Yep. Not just 45, 45 models, exactly. Now, this sounds crazy, but one thing about this one is if you're going to discriminate zeros from ones, you don't need to include the 2s, 3s, 4s, or 5s in that, right? So you actually can train each model on a smaller amount of data. You can train it on just the ones that are really 0 or really 1. So for some models, they don't scale well with the number of images you're training it on. So in fact, you save a lot of time by having a smaller training set. So having more models with a smaller set in each model might be an advantage, depending on which model you're using. And support vector machines have this property. They scale poorly with the size of the training set. So that would be a time when you might want to do 1 versus 1. Most of the time, 1 versus the rest is preferred. I would think that's kind of obvious because having just 10 models to train is probably going to be faster and easier than having 45 models to train. But that's the way it is. All right. Is there a math shortcut to represent 1 versus 1 like factorials? Well, yeah, it's this one. It's n times n minus 1 over 2. And this is actually something Gauss developed when he was like 6 years old. Anyway, it's a well-known trick to add numbers like this, a series of counting numbers. All right, and so a support vector machine is one that will automatically use 1 versus 1. Now, this library we're using is very smart. So when you choose a type of model, and we're going to cover the types of models next week and in the future classes in more detail, then it will figure out which kind of system, 1 versus 1 or 1 versus many, is best to extend that to a multi-class classifier. So you don't need to tell it. So if you choose an SVC model, it will figure out that needs to be 1 versus 1. And so you fit. It just automatically fits it, and you end up with 1 versus 1. And if you print out the scores, you'll see 10 scores. So it doesn't have 45 outputs, it has 10 outputs, which is the probability of it being a 0, a 1, a 2, a 3, and so on. And so you can see here, there's an 8.3, so it looks like 0, 1, 2, 3. It looks like this is being detected as a 3. That's the biggest number. But it looks like it thinks maybe it's an 8, but a 3 is winning. And this one's, the 9, they're at 5. All right, this first model is really a 5, although a 3 was close and an 8 was close, but a 5 won with 9.3. And that's the first image in the set, which is really a 5. So then the support vector machine is another model, which it automatically chooses 1 versus the rest for that. Excuse me. The support vector machine here would like to be a 1 versus 1, but you can force it to use 1 versus the rest if you want to. You can not make it choose the default, which it considers best. You can import this 1 versus rest classifier and then use it on your model and force it to do it that way. And so you can override these. All right, and so, so here's the support vector machine doing 1 versus the rest, and stochastic gradient descent. This one, this should be SGD. It's not a support vector machine anymore. This is, I think, an SGD. Yeah. All right, anyway. So uses 1 versus the rest with 10 binary classifiers, and you see it incorrectly predicted a 3. 1800 here is the biggest number, but the next runner-up is minus 1386. So the right answer is 5. It chooses a 3, but a 5 was pretty close. So that's what happened in that one. All right. And now to analyze the error of a multivariate model. The confusion matrix is not just 2 by 2 anymore. The confusion matrix is 10 by 10. You have the true label and the predicted label, and then you can count how many instances there are in each one. And of course, if most of them are correct, the diagonal will have most of the big numbers. So here's the number of ones that were correctly identified. It was really a 0, called a 0, really a 1, called a 1. All the rest of these are errors. And as you can see, they vary quite a lot. Like there's a lot of errors in this column. So apparently it has a high chance of predicting an 8 when it's not an 8, and a much lower chance of predicting a 6 when it's not a 6, and so on. So you can see this. You can get a complete description of your error pattern here. All right, now here's another problem. If you count the positives, you'll see cell 5 has 4,044, the rest have 5,000, so that might make you think 5 is being poorly predicted. But the problem is this is just a raw count of images, and the original data set probably didn't have an equal amount of every image. It's a random set. So you don't really know if this low number here means that the 5s are particularly hard for the model to classify. So what would be better would be to take this cross matrix display thing, confusion matrix display, and add a parameter showing put it in percentages. Now it'll rate them by percentage, and now you can see that in fact the model does have a problem with 5s. Now that you got rid of that confusion, you see it's 90, 95%, 88%, 82%, and 86%. 5s are apparently very hard for the model to pick up. It has a high chance of misdetecting them as, say, looks like it often calls them 8s, 10% over here. So the 5s, it gets wrong. A lot of time it calls them 8. And it looks like the 9s it gets wrong, and it very often calls them 8. So that's, you can see more details here, that's low correct positive for 5 was in fact a real thing and not just an artifact of sampling. All right. You can also plot just the errors if you want to. You can put in this sample weight, which is going to be 1 for the errors and 0 for the others. So it'll just zero out the diagonal to get it out of the way, and now you get percentage of the others. So of the errors, now 65% of the errors are here. You see most of the errors are when you call it an 8. The most common thing it does is when something is sort of scrawled, it guesses it's probably an 8, which kind of makes sense. An 8 is sort of what fills the whole screen. So you can see that it's not that the errors are evenly distributed at all, it's that it has a huge, the main problem it has is it accidentally determines things, calls things 8s when they aren't. And you can also normalize your errors by columns. So you see 100% this way, and then you'll see which digits are more likely to get wrong, and it looks like 9s. Yeah, 56% of the misclassified 7s are actually 9s. So if you called them 7, but a bunch of them were actually 9. So that's a thing to know. All right, so this is a way to analyze the errors. All right, and here you can also just view example images. So here are just examples of things that are called 3 and called 5. And so these ones are correctly identified as 3s. These are correctly identified 5s. These are things that were really 3s, but were misidentified as 5. And you can see they're sort of scrawled. You thought this was a 5. And here's 5s that were misidentified as 3s. So you can look at this, and you can see here's a 3 that's correctly identified. This 3 is badly identified. You see, it's just kind of because this middle dot is a little bit to the left. The main difference between a 3 and a 5 is the location of this junction. If you grab this and move it to the left, you get a 5. So it's the location of this crossover point in the middle is the main thing that determines a 5. So you might wonder if your model is just looking for like the brightness of this area here, and if it's dark it calls it a 5, and if it's bright it calls it a 3, and that's why it's getting these 5s wrong. So then you might want to train your model to handle that by taking your original images and shifting them and rotating them a little bit to create, this is called data augmentation. When you take your original data and then you modify that data and feed that in, so you use altered data and add it to your data to make your model more flexible. So you should train your model to handle if things are tilted or shifted to the left a little more in the hopes that it will get better at this discrimination. That's a technique, data augmentation. And this reminds me a lot of Stable Diffusion that I was talking about before, which does this incredible thing of if you want to get an image from Stable Diffusion of a Picasso, You just get some starting images that are real Picassos, and then you slowly add more and more noise to them until you have 1,000 copies of each image created with more and more noise, and then you train your model to de-blur it. And then to make a new Picasso, you start with random noise and just de-blur it into a Picasso. And that's another issue where you have this, you started with just a few images and you turned each image into 1,000 images with data augmentation by computer training them. And there's a negative side of this too, which is hitting the press all over the place. When the large language models were trained on a whole bunch of internet traffic, internet words they found. But the problem is now a large amount of the words on the internet are created by large language models. And they have shown that if you trained large language models on text that was produced by large language models, they deteriorate really fast and produce nonsense, as you would imagine. So people are really worried about this, that as we pollute the web with a bunch of large language model generated content, we are going to lose our training data, and the large language models will degrade. So anyway, those are examples of automatically created data and the consequences for training. And then there's a few other cases like multi-label classification. Suppose you're not trying to recognize a digit, but you're trying to recognize like features in an image, like a Tesla is supposed to look at the road and it's supposed to say, okay, this is the stripe in the middle of the road, this is a car, this is another car, this is a dog, this is a person, this is a traffic cop. It's not like it only wants to see one of those things. It wants to see all those things at once. And that's the similar issue. So you want to, instead of having one category per image, you'd have multiple labels on the same image. That's multi-label classification. So in a simple case here, we're going to use that same MNIST data set, and you can have two labels. One is the digit is large, 6, 7, 8, or 9, and the other is digit is odd. So those are two labels, and both of those labels might be true at the same time. That's a simple case. And so you can train on that. Large and odd, you have Y, and then you just train your model or multi-label classifier. We're using something called K-neighbors classifier. And so now it predicts that the first image, which is 5, is false true, which means it is not big, but it is odd. So that's correct. And so you can evaluate your multi-label classifier. You can get the average F1 score across all labels. That's one possible number. There's 97%. This would be appropriate if all the labels are equally important. Of course, if you think about the Tesla, they probably are not equally important. Like perhaps the pedestrian should be more important than the cars. Perhaps the police car should be more important than the other cars. You know, it might not be true that your best measure of performance is just the average F score. And so SVC does not natively support it. So one strategy would be to train one model per label. But if you did that and ran them separately, they wouldn't know about dependency between the labels. For example, if you have determined that it is large, then it has a much more likely chance of being odd. 2 out of 3 of the large numbers are odd, but only 1 out of 2 of all the numbers are odd. So if you decided it's large, it's much more likely to be odd. So you should really take the large output and use that as an input for the odd detector. And that's what a chain classifier does. It will train the models in sequence, and it will feed the labels from a previous model into the later models to help them. And this is a lot like what we talked about in, I think, the first or second class, where we had this data about California housing prices, and we found that by combining fields to make a new composite field, we actually get a field that was more useful at predicting the outcome. So, and then another one is multi-output classification, which is where you have labels and multiple labels, and the labels are not just true and false, they have multiple values. So if you want to remove noise from an image, you have the input is a whole bunch of pixels from 0 to 255, and the output is a whole bunch of pixels from 0 to 255. So you don't just have true or false, you have multi-values for each output and many outputs. So that's the most complicated situation, where you're taking noise off images, like I was describing Stable Diffusion doing. So, all right, that's what I wanted to show you here. Let me stop this video since I haven't got the cahoots.